Hello, it's Keith here, and this is the second of the simple series where we're going to be looking at very basic self-contained examples, just a single assembly file to do a simple task on each system. This week we're going to be looking at the ZX spectrum and we're going to learn to draw a simple bitmap. Well, let's start off by looking at the example we're going to be running today. Now here's the first example. We're just going to show a single smiley face, an 8x8 pixel tile kind of square here. And then beyond that, we're going to extend it just a little bit into drawing a slightly larger sprite of our Chibico character here. So there's our Chibico. So that's what we're going to be doing. So this is just a very simple beginner example for if you're trying to create a game and you want some graphics, which is going to be something you're going to need. This should hopefully be a good introduction for something for you to build on, just to get started. And as I say, this version, everything is in this file. There's no includes of any kind, so if you're not using the same assembler as me, hopefully this is a good place to get started and start building something a little bit bigger. Now this version here, we're including a bitmap file here, so it's slightly more complex, but again, pretty straightforward. Now the graphics for today's example were converted with my Sprite editor. It's just here. This is a free open source program that I use in my tutorials. Now the original file was 4-color, but if we go here and we go to the spectrum color option here, we can then export this as a 2-color bitmap. So we just go to File, Save Raw Bitmap here, and we can save that as 2 colors. So that's how you can create the graphics that were used in today's example. And so hopefully this will be something you can make an easy start on. So how are things going to work on the spectrum? Well, the tricky thing with the spectrum screen is it's like some of the other systems. The lines aren't consecutive, so line 2 is not directly below line 1 in memory. So when it comes to calculating a memory location in screen memory from an XY position, we have to be a little bit tricky. Now, we're going to go over the getScreenPos command, which is the command I've written to convert an XY coordinate in BC into a memory address in HL. If you don't understand this though, you can just use the code that I'm giving you in today's example. So please don't panic if you're getting confused, just stick with the code as it is. But I always try and explain how things work and why. So we're going to go into the details and it's going to get a little bit confusing. Now basically our addresses in Spectrum memory are of course 16-bit because the Z80 has a 16-bit address bus. Now the bitmap memory starts at hexadecimal 4000. That's why the top 3 bits of the memory address will be 010 because that's the equivalent of the 4 at the top nibble. Now the remaining memory address is calculated from the 5 bits of the X coordinate. The coordinate will be from 0 to 31 in bytes because that's counting the screen across in bytes, and then the Y coordinate counted in screen lines is actually split up into different chunks, which is very weird, but I think maybe there's a reason for it. So the bottom 3 bits end up here in the top byte, which will be in the H part of the HL pair. The next 3 go here, and the final 2 go here. Now, why is this, you might think? Well, it'd be a very good question. I think the reason is if you're drawing within an 8x8 aligned character block, then to move down a line, you just increase H. But when you go over that, it gets quite complicated. But I've got this getNextLine command that's going to sort it all out for us. So anyway, as I say, all that you need to really take away from that is the configuration of the address is a little bit complicated, but we've got a command that can make it easy for us if you're struggling. Now that's the black and white data. There is also color data stored in a separate location. This is a hexadecimal 5800 in memory, and fortunately this is much more straightforward. The lines are consecutive below each other. There's 32 blocks of color for each line, and then each of these blocks is 8x8 pixels, and then when we move down a set of blocks, so effectively 8 bitmap lines down, then that would just be 32 bytes on from the first line. So effectively we just multiply our Y position by 32 if we're counting that Y position in blocks, and then add the X position. Now let's have a look at that in actual code. So here's our getScreenPosition command here. As I say, I've kind of tried to optimize this to make it efficient, which unfortunately doesn't make it necessarily as readable. But you can see we're splitting out these 3 bits here, these 3 bits here, and these 3 bits here. And we're effectively shifting them around, bit shifting them around to get them into these positions. And then we're adding the hexadecimal 40 here to get the base of the screen memory. Now, if you were using a second buffer and your screen was at C000, you'd want to change this. but generally speaking this should do it. Now I made a mistake earlier, I said HL. This version actually uses D and E, not H and L, but apart from that, as I say, it will work just the same. Now this will calculate the initial position, but when you want to move down a line you could use this again, but it's going to be slightly more efficient to use this get next line command, which will move DE down a full equivalent screen memory line and work out the position of that new line. And again, it's having to split things up into sections just depending on the current line position relative to the memory address. So we're not really going to go into any more detail on these, but we will see them in use. Now the get color mempos command here, what this does is it ignores the last 3 bits of the Y position. That's because, as I say, it works in 8 pixel tall blocks, so the 0 to 7 of the Y position are going to be ignored, and so this is working out a block number, and then we're effectively multiplying it by 32 by doing some bit shifting here, and the result again, once we've added the X position in DE, will be a memory address. And when we want to move down a line, you can see that just here, we just add 32 to E. If we've gone over and overflowed E, then we need to add that overflow to D, because when we're working in 16 bits, if we're doing 1 register at a time, we have to cope with an overflow, so we're checking for a carry there. So that's the very basics of how we're calculating a memory address. Now, as I say, I'm kind of thinking you're probably going to look at that and go, oh my god, that's really confusing, I don't understand it. Well, that's fine. As I say, this top bit is using those pieces of code as a simple example to draw our smiley face. So how do we draw our smiley face? Well, what we need to do is work out an XY position. So we're putting the X position, 16, 10 in hexadecimal here, into the X pos here in B. And then we're setting the Y pos in C. And that's in lines, pixel lines effectively. The first one's in bytes. Now we call get color mempos, which will calculate the memory address of the color for that block. Let's say in 8 by 8 blocks. Now, because our smiley face is 8 pixels and that's a single block, so we're just setting it to a fixed value here. Now this is the magenta here, and we're storing it in DE, which will, after this command, be pointing to our position on the screen. So it's calculating this position here. Now I'll just prove this to you. If I change this to, if I add an extra 1 here, and then I change this to just 5 here. Now you can see we've got a white color because we've set these 3 bits here, which is defining it as white, and we are much further to the left because we're now only 5 bytes in from the left hand side of the screen. So we can change our color by changing the value we write to here, and we can change our position by changing these values here. Now this is all of the code to set the colors because our entire tile is just one single block, so that's all the code. There's no loops, there's no larger area fills, that's it. Now when it comes to the bitmap data of our smiley face, this is the bitmap for our smiley face here. It's 1 bit per pixel, so where there's a 0 the color will be the background, and where there's a 1 there'll be a foreground. And you can see here's the eyes, these zeros here, and these zeros here are the smile, and the ones are the circle of the face. So you can see our smiley face is represented in the bits here. So when it comes to actually getting it to the screen, what we do is we run the get green pos command again with the same BC value. They were unchanged in this section, and that will calculate the new DE for the bitmap data, which is from hexadecimal 4000 onwards. Now what we need to do next is we need to loop around. There's only 1 byte per line, but we've got 8 lines, so we're setting B to 8. We're reading in a byte from HL. That's the source data of the test sprite here. We've just set that there. We then store it to DE, which is our screen destination in the bitmap memory, and then we increase HL. Now we don't increase DE because we actually need to calculate the line down after each time, because as I say, it's quite complicated. So we run get next line to do that. Now if BC had been unchanged in all of this section, we could have used get green pos again to completely recalculate, but get next line is quicker, and it means we don't need to worry about these. Only DE needs to be correct. So get screen next line will move us down, and then we just repeat back up to here until B reaches 0, and that's all we need. Now if our tile was taller, we could just change this to 16 and run again. Now we've printed some corruption here because our test sprite is too short, and you can see the second part isn't coloured because we only coloured 1 block there. But you can see that just increasing the height is very easy, but if we want to increase the width, then what we're actually going to need to do is alter this code here. And that's exactly what we've done in this second example, which prints our Chibi-Ko characters to the screen. So here's this example here. So now we're doing a 6x6 in 8x8 block tiles. This is a 48x48 pixel, but as I say, there's 8 pixels per block horizontally and for color blocks vertically as well. Now we're starting basically the same here. We're selecting position 16,16. Now we're getting the color mempos here, but we've got to back up B, C, because this code is going to change B and C, and we need them to be the same when we get the screen position for the pixel data. So what we're doing here is we've got to set all of the blocks of our sprite. Now our sprite is 6 color blocks tall and 6 color blocks wide. So we are getting our color mempos here. We're setting the accumulator to our magenta here, and then we're writing the color magenta to the destination that was calculated by get color mempos, repeating for the blocks along the line, and then we're getting DE back, calculating the next line, and then repeating for each of the lines. So B is the width here, and C is the height here. Okay, so that's defined our colors, but we need to do the bitmap data still. I'll just show you if I put a DI halt in here. You see, by this point, we've defined our colors, but we've got no bitmap. So we're going to do the bitmap second. Of course, you could do it the other way around if you preferred. So this time, again, we're going to use get screen pos to calculate the DE memory address that we're going to write to. We're going to get the test sprite data in HL. Now, we're going to use B and C as the counter, and I'll tell you why in just a moment. But we're going to use IXH as our vertical count. IXH is one of the sort of extended registers. We can use it just fine in this example. So we've got 48 pixel lines to draw, and we've got 6 bytes per line. Now we've got our inner loop here. This is going to use the LDIR command. This copies BC bytes from HL, which is our sprite, to DE, which is our memory. Now LDIR uses both B and C, which is why we've been unable to use C as our counter here. So we're loading BEC with 6, we're doing the LDIR, and once we're doing that, we're calculating the next line, and then we're repeating till we've done all of the lines. So this code is basically the same as the last example, just with this extra BC and this LDIR doing the copying. Here we didn't use an LDIR because there was no reason to do a loop here. But the benefit of LDIR is going to be relatively minimum in this case, but the bigger the sprite is, the more efficient it's going to get. And I thought it was a nice opportunity to use it. So there we go. That's how we can calculate our screen positions and draw a coloured sprite onto the screen. Now, of course, in this example, the entire sprite is just a single colour. Now, you might want to make each of the blocks of the sprite different colours. You know, maybe you would want the hair to be magenta, and we could have like the shoes as cyan or something. Yeah, we could do something more complicated, but we would actually need a second bitmap to do that because we've only got our bitmap data here. You'd need a color map, and then you'd need to load in from the color map and write that to the color memory here, and that's outside of what I wanted to do in this example. So yeah, that's something you would certainly probably want to do in a game, but I think in the first case you're going to be just worrying about getting some simple graphics on the screen, and that can be something you can add later. Anyway, I hope you found this interesting. If you're interested in the Spectrum, hopefully this was something that's going to help you get started. As always, you can download the source code for today's example, get it from my website. The development tools I use, the scripts and the Notepad++ with the configuration to automatically compile things, you can download that too. So if that helps you out, go ahead and grab it. Hope you found this interesting. Please like and subscribe because I've got more Spectrum stuff coming, and I'm even working on the Spectrum Next at the moment. Thanks for watching today anyway, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code and development tools for 6502, 68000 and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots. Tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.